going to take a count, and we're going to figure out who left. So here's some performance numbers. I'm just actually going to try and kind of blast through this pretty quick. There's just like a few slides left. This was done with our .4 implementation, and like I said, we really do try to keep these legit, and just so that we can see the performance. And this is what we saw with our .4 implementation, where we're now going almost to .8. So it should be better by now. But the green one is the one where, if you look over there, it's actually accessing data in the memory grid. The other one, the Jet 04, the blue, is when it's actually accessing HDFS and reading its data and syncing its data back down to HDFS. But even with HDFS, we're faster than Spark, and we're faster than Splink. Call them together. So these are just some of the ones that we've done, and then this is the latency one where obviously we're blue, and small is better on this one because we want less latency. So this is the kind of performance we're seeing, and we're pretty happy with where we are as far as how it all worked out. So the architecture, I think I've talked a lot about DAGs and vertices and edges. This part kind of goes, I'll just quickly go through this. This part kind of goes into how we do it. And basically each of the those little nodes, the circles on the diagram, they get distributed out. But what we've written kind of, where does it say? This next one's probably better. You didn't want to use native threads or JVM threads because they don't switch as fast, and you kind of give up control. So we implemented a layer on top of that we it's our own implementation of kind of what are called green threads. So that's how every one of those little tasklets is assigned a green thread, and it executes, they all execute in parallel at the same time, and then the underlying engine kind of swaps that out with the real threads. So, that's how we can distribute much better, and we can sort of control the execution of each one of the nodes, which is the tasklet idea there. So, this is just a lot of words to talk about how we did that. I don't know that it's that important. I want to hurry up and get to the demo. It is important to say there's a couple concepts in there that are important. Back pressure, like when your events are flowing in as fast as they can go, and if there's a certain process that can't keep up, like how do you control that? You can either sort of start dropping events, or you can refuse to connect or something like that. But we use the concept of back pressure because in between, and I'm just going to switch to this one, even though it doesn't really talk about what I'm talking about. In between each one of these tasks, we have that INDG buffer, right? So we have control over when that gets read and when it gets pushed. So when a processor is starting to get backed up, it lets the underlying system know, hey, I can't take anymore. And then from that buffer part, it tells the downstream or the upstream actually processor, you need to back off because we can't take anymore. So that backs up all the way through, and then hopefully not all the way to your source, because if the source is continuously putting in and you can't keep up with it, then bad things are going to happen anyway. But generally speaking, we can deal with bursts that way and just distribution across, because when one of them backs up, it'll actually start to get serviced by other processes that are running and may have more capacity. And also with that green thread implementation, we put in the work stealing idea, where every time one of the processors goes to check the queue and see how many it's got, it actually checks its neighbor's queues, and if they have more, it'll steal from their queue and process it, because the idea about how all this works is that each one of those is independent. So it can go grab the same job off another task's queue, and that way we can sort of distribute the workload and make sure that we're consistent. And as long as you sized it right, then you should have no trouble keeping up with your job. And this is just saying how things are distributed. There's two APIs. The first one we built was this DAG API, and that's because we really needed that kind of control, and we needed the ability to really do some fine tuning as to how this thing was working. And it's fine to use it. The problem with it is that it's pretty complex, and it can get sort of deep in the weeds before you know it. So we built on top of that, and this is what's delaying the 1.0 GA version, is we built on top of that over the last several versions what we call this pipeline API. And that's where we brought it back to extending the streams API so that it's really more intuitive to use and easier to use, and it's more comfortable for anybody that's used to working with streams. Now, you can still always drop back down and go to that lower level API if you need to, and sometimes there are reasons why you might want to do that. So they're both available, but I would suggest anybody starting to use the pipeline API, because it's going to keep getting better. And ultimately, it just gets translated into a DAG anyway. They both do. So it's the same kind of code that's going to execute. So the windowing, I talked a little about windowing. I'll take a second or two just to go over it. This is a topic you can get pretty deep on if you want to, but suffice it to say that when you have an infinite stream, you have to figure out, okay, how am I going to pick the events that I want to process? If I'm doing aggregations or I'm doing averages or summations or anything that I'm doing, I have to figure out, it's never ending, so I have to put a stop on it. So we built out of the box. These fixed windows are the simplest. It's just boom, boom, boom. It's also sometimes called tumbling window. And you just sort of, you just have this window and you cut it off. Now there is the concept of a watermark, which is where you try to say, I'm going to wait a little bit for those late events and then stick it in here before I process it. I've heard that referred to as a black art, because it's better to wait because you get your events, but it's also worse to wait because you increase your latency. So there's this kind of trade-off between the two. So you just got to figure out what fits you. So the fixed window just kind of tumbles, does each one. Sliding window is, like it says, there's a window and it just slides by blocks along the time, and each time it aggregates. You have to figure out how to put the things in the window, but the sliding window is the most common. It usually fits what everybody's trying to do. And then the session window is where you have events, and events are correlated by a key. Usually you're doing some kind of group by key. And if you have related events that run in, you might have a session window where you keep that alive and then you do whatever calculations. And if that window expires, then you just kind of close that session, do aggregations or whatever. And then if another event comes in, then you just start a new window, with that key. So those are the three we provide out of the box. But like I said, you can always implement your own because there's just an interface and you can plug it in however you see fit. That's the watermarks. What I was just saying, that's just about what to do when events come in late. Even though they're outside of the window, do you want to still put them in before you start processing? And you just have to figure out what you want to do there. So here's some things about fault tolerance. I think we really already talked about it. And yes, I'm going fast because I want to get to the code. I think everybody's sick of looking at slides, but there's a lot of stuff to cover. So, we have that underlying INDG fault tolerance. Jet uses the snapshots. If the node fails, it'll get restarted, and that happens automatically. And then you can increase the size of your cluster dynamically, and it'll execute the job. You can pause the job and then restart it, and it'll start using those new resources. Distributed snapshots. I mean, that's the snapshotting. Like I said, it's going to make copies, and it is resilient in case of failures. And this also talks a bit about the exactly once versus at least once. Exactly once is actually a pretty hard problem in a distributed environment, and we have built that, and it's just you flip a switch and turn it on. However, it does pay a performance price, because it has to use snapshotting to make sure that it knows if events have already been processed, not to process them again. All right, so here is the flight telemetry piece. So I have it running in the background already. Actually, no, I haven't started the jet part. I wanted to show that. So let me set this down. Hopefully that doesn't make too much noise. All right, so this works by it has a jet process, and the source, like I said, I guess I'll show you the code first. Well, maybe not. Let me just talk about it. The source is actually that FAA, I forget what it's called. It's not FAA. It's a worldwide tracking system for all the planes that are in the air, and you get the tail number and the plane identification. You get its lat and long. You get whether it's ascending or, well, actually you get its altitude, and then we calculate whether it's ascending or descending. So what this does is it retrieves all that data dynamically live via the web, and then as it comes in, we've actually pre-populated some tables with airport latitude and longitude and actually kind of made a sort of a geofence around it because we want to pick certain airports that we're going to pay attention to. And then it has the known sort of CO2 emissions of the engines on that particular model of airplane that for when it's under full power for taking off, and also the noise, the decibel level, because that's all published information. So we preload the that sort of static noise level information and CO2 level information. Then we go in a real-time basis, or at least on a polling basis. I think it's every 10 seconds. We go fetch all the airplanes in the world that are flying. We run them through a filter to see which ones are under 3,000 feet, I believe it is. Then we do a calculation, like an aggregation across that airplane's tail number, because those events are coming in, and we correlate on the ID, and we can compare the different altitudes to see if whether it is ascending or descending. And then we also filter it based on those airport lat and long coordinates to figure out if it's, what airport it's at. And all of that, we kind of come down with, okay, this one's taking off, this one's landing. If it's doing that, what is its CO2? We go through, I'll show you that pipeline. And then its sync is actually a graph fauna dashboard and little graph database. So when I show you this is that little, it's just a simple dashboard. Let me make it a little bigger. Right now it has no data because I haven't run the application. Here I have this application. I have Maven, so when you look at up here, it's this flight telemetry, the Maven dependency. It's just got Hazelcast, Log4j, and the stuff comes in as JSON, and so we use this little Python library to parse it. So it drains it all to that. So I compiled it with Maven, and now if I just run just exec Java for Maven, I'll run it. And this is going to start one node, and you can watch it. First it starts a node. More nodes start, and you would see them join. If you see right there at the top, well, it's already off, but it says it's a cluster of one because I only ran one. That's the DAG that just was constructed from the source code that I made. And then that DAG was constructed and then submitted to the cluster somewhere, execution and start execution, hold. So they're pulled 55,220 aircraft. I guess at any one time in the world, there's about 5,500 aircraft in the air. So yeah. So it is now, you'll see it'll print as it goes through. You can see it's got to go through and kind of catch up because it's getting stuff that since it was off, it doesn't know about it. But it will go through and it will start. It's dropping some of the late events. That's the window that I set up. This is a 3-minute window, sliding window with 30-second blocks, which is how it kind of slides. And it will drop. You might see some information where because of the watermark, it's getting rid of ones that are old. But now it's starting to detect which ones are landing and which ones are taking off, and whether or not they are in that geographic area. And when I go back and look at this thing, you start to see some events flowing in. And this will start to tell you this is CO2 emission and this is the max noise in the airport, the neighbors around the airport. 2 have taken off from Tokyo, 1 has taken off from New York, and this is all happening right now live. This has happened in the last few minutes. And these will continue to grow and start to track this. And as we go longer, I believe the window is 3 minutes. I can look at it, something like that. It will start to do the aggregations of what's happened in the last 3 minutes. So I can leave this running in the background. Do you guys normally look at code? Because when I'm talking to a customer, I always want to make it look easy, so I don't normally show code. So, but here it's like, okay, this is a Java meetup, so I should probably show. Let me make it as big as possible. Can you see that? This is just somebody took a lot of time, and I think they hand did this. This just sort of shows you what this DAG is doing, and then below that is the code. So it gets that flight data source. It filters the aircraft at low altitudes. That's a filter for under 3,000 feet. Assigns airport info to that flight because it'll know from the lat and long. The watermarks are about what to do with that event, like how long do we want to wait and just drop it when it's out. Calculate the linear trend, which means is it going up or is it going down? And it's doing that because it's going to group by everything that has that event with that tail number it's got. And then it's going to assign a vertical direction. And then we look at that CO2 information and enrich it, calculate different things, and sync it down to the graph sync. That's pretty much what it does. If I look at the code, can you see it? Can you read it? Or do I can make it bigger. Is that good enough? No? I got one no and a lot of yes. I'll click one more time. How about that? Is that better? If I get it too much bigger, we won't be able to see it all at the same time. So if you look at the main NuGet instance, the first step there is it's calling build pipeline. And that's because it wants a pipeline object. And then these other two things are actually just adding listeners because it wants to print out. That's what's printing on the thing. It adds what we call an event listener or an entry listener to the actual underlying table in IMDG. And then it just sends a print line message. That way when it's scrolling, you can say new one taken off, new one landing, all that kind of stuff. Where it really gets interesting is that build pipeline function. I got to take these off to look up there, and I got to put them back on to look here. So when we look at this build pipeline, so the first thing it does is it says pipeline create, and it's just a static method to create a pipeline. It's not doing anything yet. Then we build the actual DAG. That's what this is doing. It's building the DAG. The first thing we create is a sliding window, 60-second window, 30-second block. So it's going to slide 30 seconds each time, but the calculation window is 60 seconds, right? The first stage, so when you're building a DAG in code, there's really kind of there's three things. There's a source, there's a stage, and then there's a sink. And everything in between is kind of the same thing. In this case, the first thing it's doing is building that stream stage because it's a streaming data source. And you can see the draw from. And that's where there's actually a little method to say stream the aircraft, and it handles like connecting to that URL and giving it the polling time, and then it's got the JSON parser and all that stuff. We don't really have to worry about it. But it's just saying, okay, here's my source. I'm going to draw from that. I'm going to add a timestamp, which is where it's looking at that event, that aircraft event, getting the position time and seconds to millis. I forget what the seconds are for. I'm going to filter it. It's not on the ground. If it is ground, that means it's not moving. So let's ignore that. I'm going to get the altitude. If it's greater than 0 but less than 3,000, then that's going to be true. And this is sort of a standard stream thing where if whatever is true, the event is going to flow through, and if it's false, it's just going to drop it. So basically, at that filter, I've just gotten rid of all of the aircraft events that are on the ground or they're up high. They're not landing or taking off. If they're more than 3,000 feet, I mean, they could be landing, but we're just paying attention on 3,000 feet. So I've just gotten rid of all of those. Now I'm going to say map flight telemetry assign airport. That's just a function that gets handed you have to remember, as this flows through, everybody's using Lambda and functional kind of stuff. The event is flowing through to each of these steps. So when I say map flight telemetry, I'm calling that assigned airport, but that method has a signature, an aircraft event. So it's, the system interprets that and it's smart enough to know that's what I'm doing. And that's just Java. That's not Jet. So then I'm assigning an airport, which is basically I'm enriching the aircraft information with the airport data that I've already loaded in a table. I'm setting my sliding window on this stage. I'm adding a grouping key, and that's the aircraft get ID. And that's important because what that means now, and you got to remember, the system is keeping track of all these different DAGs, and they're all running the same. When it does an aggregation, which is the next step, it's going to do it on the events that are grouped by that key, which means it's going to do it for every single airplane that's running all at the same time, but independent of each other. That's how we get that linear trend, because you say, okay, I'm going to do this aggregation for all the airplane events that have tail number, 5, 6, 7, and then it'll say, okay, well, when I got the last one, it was 3 minutes ago, and it was at 3,000 feet. And now it's, a minute later and it's at 1,000 feet. Oh, so it must be going down. That's basically what they're doing. But it knows to only do it for that particular aircraft because we told it that's your grouping key. So as this comes down, now I do that aggregation, and that's the end of that stage, right? And it seems like that's kind of the end of it. But that's where these other stages come on. And if you watch, this is where you can have multiple edges and the vertices that come out. because that's the stream stage, that's the starting point, right? And it's a beginning. All of the rest of these are where we do other things, but if you notice, they're created from flights, and that one is named flight. So all of these steps that we add later, you create it. You say, if you look at it here, it says flights. It says flights.filter.get. Eventually, it attaches this stage to that first stage flight, and that's how it knows to kind of go to the next one. And eventually, we get down to a sync at the end. So as we go through this, you can see that second one. This is the filter for filtering ascending flights. That was that little stage in the drawing. The next ones, we're branching off. We're going to branch off, and we're going to get landing flights. And these two actually have drain twos within that section, which means they're going to drain it to an underlying IMDG map, right? We're actually splitting off a little data to keep track of it. We have several different syncs. Then, and these are all still attached to that flight. So they're basically branching out from that first flight. And then so here I'm getting max noise. So I'm figuring out, what is the noise that this particular flight is making right now. So I do a map, I get the value, I create another sliding window, I group it by the airport code. And that's where I start to look at an event that says, is this part of an airport that I'm watching, because I have that enriched data. So it's going back and saying, okay, only filter out or group by airport, and then aggregate by the max. So I guess it's just comparing what is the max entry. Actually, that looks a little strange. And then it's just doing a map. And again, a map is just going to do some transformation of an event, but at the end, it's going to emit another event. Right? That's what a pipeline does. That's what the streaming. I know it looks kind of weird, but after you look at it for a while, it actually becomes pretty simple. It's really not that hard once the light bulb goes off. So then, in the end, we have that last stream stage that's where we're getting the CO2 emissions. Same thing as the noise, but we're just calculating the CO2 emissions, and we're doing that aggregation. This is just summing up those doubles. And that other map, that aggregates to a max. So it's just getting a maximum. I would have thought the noise would have been added, but maybe it just takes it one at a time. It just takes the loudest one. So then eventually we build this graph sync, which is going down to the graph database. That's for that dashboard. And then this is you can drain. This is one where it's on the main stage, and you're just saying drain all these syncs, all these stages, all of these stages here. It drain to this sync. It's just kind of the utility function. Usually, you would kind of do what's up at one of those up there where you actually drain it in that stage. This is just kind of an easier way to kind of join all these different things back together and dump them, because they're all the same kind of event. So that's it. I mean, that's the end of it. Everything else is just sort of the utility functions. When I scroll down, we just get into, build a graphite sync. That's just sort of setting up, it's an in-memory database that it has under the cover. So it's just sort of setting up, it's JSON, you have to convert it to JSON. How do I stick it in there? But once you build it, then you're just sending in events. And it's the same thing with the source. This is, some of these are just these utility functions where I'm just getting, I'm looking at where's I wanted to find the one where it goes out and gets the data. See, a lot of this just gets messy because it's just JSON and you're just dealing with Python stuff. But that's really it. So when you go back and look at this, we can see this is where it branched off, and we sort of assigned all these different intermediate steps. And then these are those two that drain directly because you just wanted to filter them. We just wanted to, it's just for fun. You have a map under the covers that has all the landing ones and all the taking off ones. But at the same time, we're draining all this stuff into the graphite sync as well, with the other stuff about calculating the noise and things like that. How was that? Make sense? Yeah. What's that? Oh, so the actual configuration is an object in each of the nodes that's its running configuration. So you can actually access it programmatically if you want to, and you do that sometimes for especially for configuring the objects. But to make it easier, we have an XML file that defines kind of the normal settings that's static, and it'll read that automatically at startup. And the trick there, there's a couple things. Probably the one thing you usually always have to do in an XML file is your network discovery method, because it's easy if you're on your laptop, you can use multicast, or if you're in a data center, you can use just straight IP. But if you're on cloud, so you're on AWS or you're on Azure, you've got, this other discovery methods where they can find themselves, and they got to do some lookups. So network configurations in there, and then some of the objects, like if you have standard objects, you can configure. There's a lot of stuff. That's where you set up whether you want objects to be on heap or off heap, stuff like that. But once they connect, once they come up and they discover each other, they all connect. They share the information of the whole topology of the cluster. Like I said, there's no master. They all know about everybody else. And the client too, if you're using a client, there's two ways that you can run. You can run, this is actually what we call embedded mode, where we have in the main, we actually create this new Jet instance right there. That's actually creating the node inside the application that I'm running. And that's what we call embedded mode. And it's really easy to get started. And that's how usually you OEM it or whatever you want to do. It runs kind of, in its own thread pool and stuff. But we also have client server mode where you can run these instances standalone on their own, and they run the same. They connect. They're just their own Java processes out, with other JVMs. And then instead of saying jet.new instance, you actually would say jet client get client, and then you get a client that's actually still, it implements jet instance. So after that, all the code's exactly the same. And in there you have to give it its sort of discovery protocol to the client to be able to connect to the cluster. So yeah, you can configure the entire configuration from an XML file, or you can actually set a lot of it with system properties if you want. And then if you want to programmatically change it, you can do it there. You could say from here, that jet instance, the jet, you can say jet.getConfig, and you get a config object, and then you can say, get network config, and then add an IP or something, and that'll be the running config. And then when you start the jet instance, it'll read that and start. I can't quite hear you. There's a lot of echo. Okay, so you can change the configuration on a per node basis. Usually that's a bad idea, just because it's going to be, the things are going to be distributed out across the cluster evenly. What you can do is set on a per process basis sort of its concurrency, where you can tell it how many nodes to run on, and you can't tell it which node to run on, but you can sort of set up a parallelism, I guess is what it's really called. If you were wanting to do something like, I could think of some ways where you could probably do that, but I probably wouldn't recommend that you do it, just because it's pretty much an evenly distributed system, and it wants to use all of the resources, and when you try to restrict something down, you're not going to use it. If you have something like that, I would say you can also run, it doesn't have to be an embedded cluster. You can have a remote cluster, and it can talk to a remote Hazelcast cluster. So if you wanted to do something like that, I might say, set up another cluster that does just that, and then have them talk to each other. And it can read right from that cluster if you want. But sort of like, having different servers. Because usually, we have to do a lot of work on distributing the memory partitions and handling all of that sort of distributed nature. And then the objects themselves are configured to be how they're distributed, like a map or the DAG job. And they run the same no matter where they are. So if you have like a GPU on one of them, it's going to use it, but it's not going to say, oh, this one has a GPU, run this specific part of it. Now, that being said, though, as soon as I say that, if you get to the Dag API, you actually can do some assignments about where it ought to go. You just got to be real careful with that because it's easy. You get into data hotspots and you get into processor hotspots, and not Java, not JVM hotspots, but like just data skew, I guess, is a better way to do it, or processing skew, where you might have a cluster of 20 nodes, but if you're pushing one thing over to one or two of them, and then they can't keep up, they're gonna slow everything down. The other ones are just gonna be sitting there idle waiting, but you're only gonna have the sort of the performance of the 2-node cluster at that point. So that's something to be very careful about. But you can do it if you really want to, although I don't recommend it. Mm-hmm. Yes, you're on my laptop. Right now it is. It's a single JVM and a single node. But I can run a cluster of 10, I think, for testing on these. I was doing a test where I had to read, it was a POC really. I had to read 3 million lines and do some aggregations and stuff. So I am able to off-heap memory, and I don't think it's cheating, but I figured, all right, I only have 16 gigs of RAM on this laptop. That's the one disappointing thing about Macs. I like that it's more like Linux, so I can, shell and stuff like that, but it's only got 16 gigs. So I made like 5 nodes and allocated off heap 50 gigs each, knowing that it's just going to swap, but it's got a solid state hard drive too, so it worked okay. But it's it's not resource intensive. It's really about the load. Like you can run, I can start 100 of these nodes if they're not doing anything, and they would be fine. They wouldn't take up hardly any resources at all. It's actually pretty light, IMDG and Jet both. It's when you submit the jobs and when you start loading data. So, if you load 100 gigabytes of data into memory, you got to have some place to put that. And if you load, if you run a bunch of jobs and they're all doing really serious calculations or aggregations, you got to have the CPUs to do that. Eventually, it'll finish, but there's no telling how long. I mean, that's just data size.
So this pipeline, very cool. How did you do both?
Oh, you got to ask that. No, actually, so there's a number of ways. Like when it's running this way, I end up just using standard, Java, like breakpoints and stuff, and you can watch it. You can see the values, like even in IMDG, when the debugger goes to say, what is the object, what are the pieces, and what is this list? It doesn't even know that it's a distributed map. It just treats it as a map, and I can see the values. Honestly, I don't know how it all does that, but it works. And then we have JMX, and we have like a management center that goes with Jet. We have one for IMDG and for Jet. The one for Jet's new, but it has a whole JMX connection, a whole JMX beans that you can connect to, and there's a REST API where you can get statistics and things. But it is hard. It is kind of difficult to debug distributed processes. So I end up running them, on my laptop or whatever, just making sure the logic's there, and then run them distributed.
So your source, you just pull this API, you just use back pressure, so that uses a lot.
It would queue the results into an IMAP under the covers and wait for them to be taken off. And that's where you kind of have to, so we don't ever fail over to disk. We don't dump to disk. And it was kind of a design decision in the beginning because we thought if we allow, we're all about performance. We're all about availability. That's what we're all about. If we allow spillover to disk, everybody's going to start having it happen. They're not going to know it's going to happen. And then they're going to say, why is this thing so slow? And it's because it's all being written to disk. So we don't ever spill over to disk. So that means you have to size it correctly. Now, what? You're either dropping it, well, you're going to run you're just not able to keep up with the load. I mean, you have a cluster, it's running to process this job. If it's not fast enough to keep up with the events you're putting in there, eventually something's going to die. That's just the way it goes. With the caching with IMDG, you have eviction policies and all these different ways to kick things out. So you have a subset, and you can store them to a database before you kick them out and all that kind of stuff. With Jet, you really have kind of the same characteristics because it's using IMDG under the covers. So you can start to evict actual processes and then restore them back at some point when you recover. But generally speaking, if you're not keeping up with your load, then you need more resources. That's what it's an engine. So yeah, you do have to watch that. And that's where the monitoring, and that's where, you know, there's a lot of alerting. The whole system has a whole lot of events going on in the background about what's going on. You can get access to full JVM statistics and size of the data, average latencies, puts and gets, you know, what are the size of the maps, what is the highest high and lowest low and all that kind of stuff. There's a lot of statistics you can get, and you can get them via JMax or REST. So we plug into, you know, some of those different tools. But even on our management center, we have alerting where you can set up, you know, watermarks and what's it, high level, whatever, you know, like just basic alerting around sizes, or if it can keep aggregations, and if it starts to go down for like 3 cycles at a time, it can send you an alert. You know, if your memory is at 90% usage, do alerting, things like that. So, but ultimately, with an in-memory data grid and an in-memory processing engine, you generally have to size it correctly to handle the job you're asking it to do. So, I think there were a few more slides if you want to look at them. But we don't have to. I don't know. It's up to you guys. I'm trying to think what else. Oh, okay. Let's see. Hold on real quick. There was kind of roadmap stuff. This is a little bit old. Yeah, I think that's actually it. Okay. So the dashboard. So here we are. This is what's happened in the last, I think well, this window's 3 minutes. So this is in the last 3 minutes, right? That's what it was. I think so. So this is kind of your CO2 emissions. It looks like the blue one is New York. It's going down a little bit. Maybe because it's nighttime over there. I guess they're starting to tail off. The noise hasn't changed much. And those other ones are ramping up. They're probably Europe. It's starting to become daytime over there. So, yeah. You can. You can you can add and remove cluster nodes as you will manually, and then if you have auto scaling, when they come up, they'll join. You know, we have a bunch of standard images that are out there. You know, probably more often now we see Kubernetes as being kind of the orchestration level. So we're doing a lot of Kubernetes where it starts up, and you know, with PCF we have a PCF tile officially supported, so you can run Hazelcast and PCF as a service, bind it to your LDAP and all that kind of stuff. So we do like generally what we have to figure out is when it comes up, when an instance comes up, how does it discover the other nodes in the cluster? And that's where we talk about network discovery, but that's pluggable, it's a module, and it's configurable. So if you're on AWS, you configure the AWS module to do its discovery. If we can use S3 and kind of put stuff in there. If you're in Kubernetes, you have Kubernetes. If you're PCF, it's just a different thing, but the discovery mechanism is modular. So you can always, and as new platforms come along, we'll build new ones that just, you just say, use this one in your configuration and then plug in your credentials, and hopefully it can find it. Once it finds the cluster, then it opens direct sockets to all of them. There's kind of they all know about each other. So once that's done, then it's fine. It's just that initial discovery that's usually the tricky part. Anything else? What time is it? Am I perfect?
Perfect.
That's just lucky.
All right. Thank you very much.
Yeah, thank you. Well, it was pretty slide heavy, and I really try not to do that. In full disclosure, I had a pretty cool Twitter sentiment analysis thing for Bitcoin or for actual cryptocurrency. but I didn't realize that Twitter changed their developer system. So I went to log on and I had my credentials and they wouldn't log on. And then I go and it says, oh, we've got this new thing. You have to apply for a developer account. And you have to spell out everything you're doing, and then they'll get back to you sometime and approve it. So I couldn't get that done in time, and I couldn't show you the Twitter one. Sorry.
Is the source code for this?
Yeah. Oh, I should say that. Yeah. We have, there's a bunch of stuff. We are, I mean, like I said, we are fully committed to open source. We've been open source from the beginning, and we put a lot of stuff out there. So first place to go is hazelcast.org. Here, this is our open source site, and then there's a hazelcast.com, which is our, our commercial site. But when you go here, we got a whole bunch of documents and stuff that you can look at. A lot of source code. So all of this stuff is here, and we put out a lot of documentation. We have a simulator here. There's a bunch of other stuff that we haven't talked about. But also on GitHub, we have a whole bunch of repositories for not only for the source code for the application itself, but these are code samples. There's for Jet and for IMDG that just give you basically quick snippets of how you use just about everything in the platform. And then there are in both of them those demos. Where did they go? We have so many of them. Jet code, no, that's code samples. I thought it would be at the top. Oh, come on. Did I see it? Did I miss it? I think I can. Let's hear. I just got to use two hands. Where can I search? Demo. There we are. So Hazelcast Jet demos. And then if you look, these are all in here. There's the cryptocurrency one. That's the flight telemetry one. This Jet Leopard, I'm not exactly sure. That's fairly new. I don't know what it is. Market data ingest, Markov chain generator, image recognition. I haven't used this one. I want to check it out. I think you can set up a webcam and it can start to recognize people. And then this road traffic predictor. The road traffic predictor I ran this morning, it just loads kind of static data about traffic, and then it does some machine learning stuff to tell you what it thinks is going to happen. Because it's I think the data set is certain intersections over time. So it looks at those events, it runs those in and does the calculations, over time because it's adding timestamps, and then tries to guess what the traffic's going to be in the future. But these are all up on GitHub. Just look at Hazelcast, and there's a whole bunch of repositories with more examples and code than you want to see. Like that one is this one here. Like when you go in it, it's pretty simple. You just clone it and then clone it and run it. Really, not much to it. But you'll get all the source code, and then you can go through it. And then you can go through it.
Okay. Thanks again.